Okay, take a look at this little piece of code. Now, at first glance, it just looks like a normal while loop, right? But check this out. The variable k is getting bigger, sure, but the amount it jumps by, I, is also getting bigger with every single pass. So the real question is, how many times does this thing actually run? I'll give you a hint. Just saying n times is definitely wrong. And by the time we're done here, you'll know exactly how to solve this puzzle.
Hey everyone, and welcome. Today, we're going to demystify a really core concept in programming, figuring out the time complexity of code, specifically when you're dealing with while loops and if statements. And trust me, this isn't just some abstract theory. This is the key to writing code that's actually efficient and doesn't just grind to a halt when you throw more data at it. By the end of this, you're going to have a solid toolkit for analyzing how your own code will perform.
So here's our game plan. We're going to start with why while loops need a bit of special treatment. Then we'll build up our skills by digging into three really important patterns: linear, logarithmic, and yeah, the one from that tricky puzzle. After we've got that down, we'll look at how if-else statements can change everything, and then we'll wrap it all up into a nice handy analysis toolkit for you.
All right, first up, loops beyond the basics. So why do we need to give while loops this extra attention? Well, it really all comes down to one thing: their incredible flexibility. You see, a classic for loop, the kind that goes for I from 1 to n, is super predictable. Its runtime is almost always linear. But a while loop? That's a whole different beast. You can put any kind of condition in there, update the variables in any crazy way you can think of, and that means we have to become detectives. We can't just glance at it. We have to figure out the exact moment that its condition is going to flip to false.
So let's ease into it with the most familiar case, the linear loop. This is what we call our O of n, or order of n, baseline. It's really just a fancy way of saying the work grows at the same rate as the input n. Think of this as our blueprint for how we're going to analyze the tougher examples later.
Okay, so here we've got a while loop that's basically just a for loop in disguise. The variable I kicks off at 0. As long as I is less than n, we do our thing, and then we bump I up by 1. Pretty simple. Our job is to figure out exactly how many times it runs.
The best way to see what's happening is to just trace it. In the first run, I is 0, so I less than n is true. We go again. In the second run, I is 1, still true. You can see the pattern, right? It just marches along one by one. But here's the key moment. On the n plus 1's time we check, I has finally hit n. Now, is n less than n? Nope, that's false. The loop stops. It's a perfectly predictable path.
So let's formalize this. This is our four-step analysis process. First, we spot the pattern. I just goes up by 1 every time. Simple. Second, we state when it stops. The loop terminates once I is no longer less than n. Third, we solve for how long that takes. Well, it takes exactly n steps for I to get to n. And that leads us to step 4, the conclusion. The complexity is order of n. Okay, on to our next pattern. And this is where things get really interesting. What happens when our loop variable doesn't add, but multiplies? This is where we get into something called logarithmic time, which is a massive, massive improvement in efficiency. Check out this code. The setup looks similar, but notice that one crucial change in the update step. A equals A times 2. Instead of taking baby steps, our variable is taking huge leaps. It's literally doubling its value every single time through the loop.
Let's trace this one too. After the first pass, a doubles and becomes 2, which a is 2 to the power of 1. After the second pass, it's 4, or 2 squared. Then it's 8, which is 2 cubed. Are you starting to see the pattern? After k times through the loop, the value of a is always going to be 2 to the power of k. And that right there is our big aha moment.
Now we just plug this into our four-step process. The pattern is a equals 2 to the k. The loop stops when that value, 2 to the k, is finally greater than or equal to n. So to solve for k, we just use a logarithm. K is roughly log base 2 of n. And that's our conclusion. This is an O of log n algorithm. For big inputs, this is ridiculously faster than O of n.
All right, it's time. Let's go back and finally crack the puzzle from the beginning. This is our most advanced example, a loop that actually speeds up as it goes, where each step is bigger than the last. So here it is again. The tricky part, as we said, is that two variables are changing at the same time. We add I to k, but then I itself gets bigger. So how in the world do we track this? Well, we use the same tool that's been working for us all along. We trace it out.
Okay, let's watch this one really closely. After iteration 1, I becomes 2 and k becomes 3, which is the sum of 1 plus 2. Now, on iteration 2, I is 3, so k becomes 6, which is 1 plus 2 plus 3. Then I becomes 4, k becomes 10, which is 1 plus 2 plus 3 plus 4. You see it, don't you? After m iterations, k is just the sum of the first m plus 1 numbers. This is a classic math series.
And recognizing that series is the secret to solving the whole thing. The sum of the first m numbers is roughly m squared divided by 2. So the loop has to stop when that sum, m squared by 2, finally gets bigger than n. A little bit of simple algebra tells us that m has to be about the square root of n. And there it is. That's our answer. The complexity is O of square root n. It's slower than logarithmic, but still way, way faster than linear.
Awesome. We have now totally nailed 3 fundamental loop patterns. But, loops rarely live by themselves. They are often inside other things, like if-else statements. So let's see how these forks in the road can completely change our analysis.
This is a perfect example. On the left, you've got the best case. Let's say our input n is really small, like 3. The if is true, we run one quick operation and we're done. That's O of 1, or constant time. It's basically instant. But on the right, we have the worst case. If n is, say, 1,000,000, the else block kicks in, and now we're running a loop n times. All of a sudden, our runtime is O of n. The big lesson here is that the exact same code can perform in completely different ways depending on what you give.
And this leads us to some official terms. The best case complexity is the absolute fastest your algorithm can ever run for a given input size, and the worst case complexity is the absolute slowest it could possibly be. Usually when developers talk about Big O, we're focused on that worst case, because that's our performance guarantee. It tells us the slowest our code will ever be.
Whew, we've covered a ton of ground. So let's pull all of this together into a simple, powerful toolkit that you can just pull out anytime you need to figure out how a loop is going to behave.
And here it is, your very own cheat sheet. It's this simple. If you see a loop variable just adding or subtracting, you should immediately think O of n. If you see it multiplying or dividing, think O of log n. And if you spot that weird accelerating pattern where the step size itself grows, that's your cue to think O of square root n. Seriously, if you can remember these 3 patterns, you can analyze the vast majority of loops you'll ever encounter.
So there you have it. You now have the fundamental tools to analyze these loops. But what's next? What happens when you stick one of these loops inside another one? Or even crazier, what happens when a function starts calling itself over and over again, something we call recursion? Well, that's where the next level of fun begins, and now you've got the foundation you need to start tackling those problems too. Keep digging.